I think compilers automatically use bit shifting for division multiplication on powers of 2. Standard vector bool is implemented as individual bits as far as I know, or standard bit set. The structure makes me think of a B tree. Probably, yeah, if you've got an optimizing compiler and it can see that you're working in powers of 2, that's a pretty easy optimization to make. It feels fun implementing it myself as well. Standard vector of bools, yeah, again, if we were working with an individual variable which was a bool, the compiler might have a bit of trouble. I can imagine that the compiler probably implements it properly when you have a whole chunk of bools and you know that that's coming up. Great video. Thank you. Very appreciated. Thank you from Brazil. Hey, how's it going? Brazil, very cool. Tasmania represent. Excellent choice of username, by the way. Tasmania is awesome. I've been there once. I was there in summer. It was 16 degrees in the peak of summer, and it was most excellent. A lot of cherry cider was consumed. Okay, so I've decided to reboot my series in order to focus more on the explanations and the rigor. So in this series, I'm going to be looking at macOS Metal, and specifically for this series, I'm going to be working in SwiftUI, although the concepts will transfer. First up, it's a fair question to ask, why Metal? Well, if you're using a Mac, then how's this? You don't have a choice. If you're using OpenGL, you want OpenGL functionality beyond 4.1, then for some incomprehensible reason which I can't understand, Mac decided, hey, let's just implement our own API and stop supporting OpenGL. So unlike Vulkan, where you can use tricks and hardware exploits to get performance which is on par or better than Vulkan with OpenGL, when it comes to Metal, that's not even an option. But it turns out that Metal is quite an elegant API. I would view Metal as somewhere between OpenGL and Vulkan. You do get low-level control, but without as many responsibilities. Vulkan is great, but it doesn't have an easy mode. Metal does. The concepts link up between Metal, Vulkan, DirectX, anything. You'll see that there's a convergence between the concepts. So in today's video, our goal will be to have an app with a very simple colored screen, and that's it. So what is the structure of an app? Well, like most programs, our app is going to be based on the model view controller pattern. We'll have a model, which is the underlying database. Then we'll have a view, which is all the stuff for rendering the view. Most of this series is going to be working on that view. And then we're going to have a controller, which sort of coordinates the two. Now, the lines do blur a little bit in apps, in Xcode and so on, because some of the view widgets are actually sending messages to the controller and things just get a bit messy, but this is what we're working with. And this is fine, but how is our app going to work? Well, here's sort of how our app's going to work. If you've worked with Xcode before, or Cocoa apps, or SwiftUI, or various things, you'll understand that apps are sort of widgets composited together. But the thing is that our renderer code is going to be a little bit funky, and it's going to need an adapter. So what I'll have is we'll have the app, that'll be everything, the top level controller. We'll have the content view, and the content view its job will be to adapt the renderer into something that SwiftUI can represent, can composite, can draw, all of that stuff. Yeah, then we're going to have the renderer that's going to be basically all of our Metal code, and currently we'll have no database because we're not really doing much, but in future we will revisit that. So I think it's time for us to take a pause and actually start making the app. In this series, there's not going to be a strong focus on do this code line by line. I don't think that's very pedagogically sound, but I mean, we got to start from something. So for this one, in this case, we are going to go through this together. So let me just get Xcode up. So I'll just search for Xcode. We'll open this up and we'll make a new project. I'm going to create an app. And additionally, we have a choice of these options. Actually, I'm going to go iOS. Yeah, iOS app. Why not? And we'll have to make a name for it. I'm going to call it my metal project. It really doesn't matter. Okay, the interface is going to be done in SwiftUI. The language is going to be Swift. Storage, that's probably fine. Don't include tests. Yeah, this is fine. Now I can go ahead and put this wherever I want. Yeah, pop into my Xcode folder and create. Okay, we'll go up to the top level control. And yeah, I mean, this is my main section. I'm just going to take this content view and add a modifier to it. So I'll set width to some amount. Height to some amount. I'll just give that a go. That was sort of a, let me just switch this over. So the reason I've switched that over to my Mac is just to avoid running the simulator for now, just because it's a little bit of overhead in the time that it takes to set this up. But yeah, I've just clicked run. We've got this app, Hello World. That's nice. Okay. Okay, so I'm going to make some modifications here. And like I said, I'm not going to be going into an extensive detail at this time on how I'm adapting this, but I will provide a link down below to a WWDC talk on this topic. But the idea is basically I want to take a standard piece of Swift code and adapt it to SwiftUI. So here, rather than declaring this as a view class, I'm just going to declare it as this UI view representable. That just means it's something which can be adapted to be used with SwiftUI. And in order to do that, I'm going to need to define a few functions. One of those is make coordinator. I'm just quickly going to pop off to the side because I need to make my coordinator. My coordinator is going to be my renderer class, so I'll just pop in, make a new file, and this will be a Swift file, and I'll call it renderer. Okay, so I'll leave that for now. In a second, I'll go back and fill this in. But the really important thing is that I've declared this as inheriting from a next step object and a metal kit view delegate. And that is what allows me to provide this as the coordinator. Okay, so things are looking a little messy at the moment, but that's okay. We'll get into it. So what I've done here, again, creating this UI view, and that's what we need to represent this thing within a as a SwiftUI widget. But this is creating a MetalKit view. Now, MetalKit is basically a convenience library for Metal. Under the hood, it has various objects, but I'm just going to bring up the documentation and we'll have a look at it. So I'm not going to go through all of this. You can have a look in your own time. But yeah, we have this MetalKit view. It basically gives us a view that we can work with. It requires, as it says here, it requires a metal device in order to manage the objects. I'll say a little bit more about this in a second, but a metal device is basically an abstraction of the GPU. And that is what we're doing on this line here, where we go ahead and fetch the system default device and then pass that along to the MetalKit view. There are some other things here. So we want to set the delegate. Now the delegate is the object which is called on to render things. Then we also set the preferred frames per second. Now this enables set needs display. It's a bit of a confusing name, but what it means is that when we have our underlying database and the state of our program changes, a message will be propagated onwards to refresh the display. But in order for that to work, the option to set a needs display message must be enabled. In this case, I'll go with true. We have frame buffer only, and we can actually query this. Here we go, frame buffer only. Determines whether the drawable's textures are used only for rendering. And we're not really doing anything with the texture right now, but I'll keep that as false because who knows? Okay, this is probably fine for now. The update UI view is required at the moment in order to conform to the UI view representable protocol, but I'm just going to keep it as a stub. So at this point, besides the fact that the thing just doesn't work, I'm going to flesh out this renderer in a second, but the renderer file is going to have just our metal code. And so I want to take a break and have a look at a metal concept before we press on. So the big concept that I'll be looking at today is sort of how the drawing mechanism works in Metal. There is still a bit of boilerplate code that we need to set up, initializing a few things, but the big concept is here. In OpenGL, we would typically draw things one by one. Of course, we wouldn't do it like, GL vertex 3F, like that. It's a little more sophisticated than that, but it is still sort of like draw this mesh, draw this mesh, draw this mesh. Not so with Metal, and not so with a lot of modern graphics APIs. The way these modern APIs work is as much as possible is done up front, which reduces, well, firstly, it improves the optimizations which can be done, and secondly, it reduces the number of runtime checks. So here's how it works with Metal. We have a command queue, and a command queue we could think of as an abstraction, not of the GPU, but an abstraction of the GPU's interface, the GPU's bus. So some work will be done on the GPU. It might be drawing, it might be updating the state of our world if we want to do that on the GPU. It could be heaps of things. But that all needs to be submitted on the command queue. So we start with a command queue, and then a command queue can create a command buffer. The buffer's a list. It's a list of commands. In order to record those commands, a command buffer can create a render command encoder. And there are other types of command encoders. You can have blit command encoders, for instance, if you want to move texture data around. But in this case, render command encoder. The render command encoder begins its render pass. We record a series of commands, then we end that, and then we go to the command buffer, we present it and commit it. And that actually creates the work. So with that concept out of the way, let's go back to the boilerplate. What I've currently got is we're going to have just a handle to the device, basically, which is an abstraction of the graphics card, and we're going to have a command queue. As you can see, we've gone ahead and created those things. So yeah. Now there's a few more things I need to put in just so that we conform to the protocol. One of those is the following. But we can pretty much just keep it as a stub. And then I'm going to need a draw function. There we have it. Okay, so if I read this top to bottom, the first thing I'm doing is basically fetching the area, the screen surface that I want to draw to. Then I go ahead and create a command buffer from the command queue. There we've got it. Then after I've got that command buffer, I want to begin a render pass. I want to get a render command encoder. So a common pattern here is first I want to describe the resource, and then I use that description to create it. And by the way, if you're not familiar with Swift, this business with these exclamation marks is basically indicating that all of these objects are optional objects, which means they could have their proper value or they could have nil if they have not been properly, if they fail. But this exclamation is unwrapping it and making sure that we are explicitly checking that this thing is not nil, that it's valid. Anyway, so I need to specify a few things. First up, I need to specify the color which will be used to flush the screen when the frame begins. And then I need to specify, well, when I get a new frame and I start drawing to it, what do I want to do? And in this case, I want to refresh it. And then after drawing is finished, I want to maintain that color, which is pretty much how you would expect this to work. The next thing I do is I go ahead and I create this render command encoder. This is going to have all my drawing commands when I have them. Currently I have none, right? I just begin it and end it. But implicitly, when I make this thing that begins a render pass, and it goes through the business of fetching a frame buffer, clearing it out with this clear color above, and so I at least have something. Then I go ahead and present that to the surface, and then I commit, and that pretty much sends all that work over to the GPU to be done. Now let me just see if there's anything funky going on. That should be fine now. Let's give it a go. Succeeded, that's a nice thing. Nice, okay. Very cool. Something else that I want to talk about is a real strength of Metal, and that is the Xcode Metal debugger. I'll be using this more in future, but if I have my app running right now and I go over to Xcode, and there's this little M down the bottom, I can just capture GPU workload, capture that frame, and just open it up, and then go through the business of giving me these weird errors. And then when that completes, I've got a frame, and I can do heaps of things with this. At the moment, it's not too exciting, but it's a little bit exciting. I can go over here, I can show performance, and I can actually see my occupancy, my various components of the GPU. I mean, how cool is this? The answer is it's very cool. I can go over to dependencies, and again, if I had more going on, I could see that. and I can also view memory and various objects, but I'm actually going to leave that for now. So as a brief overview of what we've got, we start off with an app, and inside the app we have various things which we can composite together. And the purpose of Content View is to adapt all this low level, next step object sort of Swift code into something which can be represented by SwiftUI. In order to do that, it's not too exciting. There's a lot of boilerplate, a lot of things we need to conform to, but there they are. And you can see the code in the repo down below. Anyway, so congrats. We've got our first app. As a next step, we're going to actually dig into the graphics pipeline, and we'll be looking at that in the next video. So all the best. That'll be it for now. I hope to see you again soon. Hope you're enjoying your journey, and that'll be it. All right. Cheers. Bye.